In this lecture, we will see an algorithm to find the kth smallest element in an array in order 1 time in the worst case. Okay. So let's first discuss an algorithm which does this job in order 1 expected time, which is inspired by quicksort algorithm. So let's call it randomized select. It takes an array A with, say, starting index P and end index R, and it is supposed to find the ith smallest element in this subarray A P to R. So the array A is indexed by, starts from P and ends at R, and we are interested in finding the ith smallest element. So the obvious base case, it will be a recursive algorithm. The idea is we will pick up pivot uniformly at random from AP to AR, and then based on that pivot we do a partition like quicksort, and then depending on I and to where the pivot element appears after the partition, we will search in one of the two subparts. Okay. So let's first write the base case. If P equal to R, then I must be equal to I must be equal to 1. Then in this case we return AP, which is same as AR. Otherwise, we pick a random pivot, say T, pick uniformly at random from AP to AR, okay, and then you partition this array A with respect to this pivot, and let the position of the pivot element be Q. So Q equal to partition A P R, and you partition with respect to T. So that means after partition, the pivot element T is placed at index Q. Okay, and let's see how many elements are there in the left of Q, which is Q minus P plus 1. So this is the number of elements. So if this is the array A P to R, and suppose here T stays after the partition, and this index is Q and this index is P, and if this is K, if this K is equal to I, then our pivot element T is the ith smallest element. So if K equal to I, then return T, else if I is less than K, that means the element that the ith smallest element that we are looking for is appears in the left part of the partitioned array. So we return we recursively call this randomized select A. I can just send the left index is P, the right index you can make it Q minus 1, and this I remains same. I need to find the ith smallest element in the left part of the array. Otherwise, if I is more than k, so else in this case I is more than k, what I do is that I return I search in the right part, and in the right part from q plus 1 to r, and the ith smallest element in the whole array is the I minus kth smallest element in the right part. So I find the I minus kth smallest element in the right part, and that I return. Okay, so this finishes the description of randomized select, and the way you analyze that the average case running time of quicksort is order n log n. In the same way, you can, if you do the same analysis, it will turn out that the average case complexity of this algorithm is order n. So time complexity of this above algorithm is order n. In average case, but in the worst case, your pivot that you are picking can be really bad, and these two parts could be really unbalanced. One part may have, say, always 1 or 2 elements, and other parts have order n elements. So in this case, your recurrence relation will become like Tn equal to Tn minus 1 plus order n. The partition takes order n. So in this case, in the worst case, the time complexity is order n square. Okay, and why this worst case can happen? Because the pivot could be really bad. Pivot element, the pivot may not be and may not divide the array into roughly equal parts. In the worst case, the pivot could be as bad as the like one part has order 1 elements, say 1 or 2 elements, and the other part has almost as large as n minus 1 or n minus 2 elements, and in that case the recursive calls will be really costly. Okay, now the whole idea of the algorithm which achieves order n running time in the worst case is to pick pivot intelligently. Idea pick pivot in such a way that the two parts after partition has some constant fraction of n elements, has omega n elements, have omega n elements. Okay, and how do I do it? And here is the brilliant trick. The idea is that here is your array A, so let lambda be some constant. We will see what what value of lambda we should pick so that our running time of the algorithm becomes order n. So for the time being, let's not fix lambda, lambda be a constant. Let's not fix lambda a priori, and the algorithm look like a magic that for this lambda it works. Let the analysis dictate us what lambda we should pick. Okay, so what is lambda? Lambda is some constant, and what do I do is that I divide this array into chunks of size lambda, and lambda is some constant. The last part may be less than lambda, that does not matter, but the other parts are equal to lambda. Okay. And so first part is, so here is our algorithm, let's write it. So step 1 is divide the array A into sub arrays of size lambda, except possibly the last one, except possibly the last one. Okay, now what do I do is that for each part I find the median. So I find the median element. Let's call it M1, M2. So M1 is the median element of the first lambda elements in the array A. M2 is the median element of next lambda elements in the array A. Okay, and so on. So till what? I will have M n by lambda ceiling. Okay, so the second step is find median of each of these subarrays. Let them be M1, M2, M n by lambda. Okay, and then what I do is that I recursively find a median of these medians. So I am writing an algorithm. So let me just write it here properly. So I am writing an algorithm which is capable of computing the kth smallest integer, ith smallest integer. So let me name my algorithm as this is not random select, this is simple select, and it takes an array A, say it takes an array A, say 1 to n, and an integer I, and it is supposed to return the ith smallest element in this array A. Okay, and now using the same subroutine, I find the median of these elements. So third step is, and that will be my pivot. So T is select I pass these sets, I store these elements in an array and pass it M1, M2. I'm writing it as a set M n by lambda, and I need to find the median element. That means okay, so middle element of this set of elements. Okay, and that is my pivot. I will argue why this is a good pivot. So the rest of the algorithm is same. So fourth is again you do again find Q, you partition it, partition A with the pivot T, and everything remains same, and depending on where Q is, you recursively call it. Here also you need to write base case. You write base case. So it is the exact same algorithm like randomized pivot. Instead of picking the pivot randomly, here is a deterministic process to pick the pivot. What is the process? You simply divide the array A into chunks of size lambda, and there are ceiling of n by lambda many such chunks. The last chunk may be of size less than equal to lambda. Lambda is some constant, so finding median from a constantly many elements takes constant time. So you find median of each of these parts. So finding M1 takes order 1 time, finding M2 takes order 1 time, finding n by lambda takes order 1 time, and there are n by lambda many such terms, and lambda is some constant. So finding each of these medians take order n time in total. Okay, and then what is your pivot? The pivot is the median of these medians. So this is called pivot is median of medians. So this is median of medians. Okay, and how do you find median of these n by lambda many medians? You can use the same algorithm, select and call it recursively to find the median of these medians. Now let's see why this is a good strategy. Why this median ensures that each part is not too small or too big. So analysis now. Okay, now so let's write these medians after sorting. We are not sorting in the algorithm. For analysis, let us sort the medians and let them called M1 prime, M2 prime, and this is say M n by 2 lambda. This is the median and this is the last. Okay, and let us draw the arrays horizontally. So those arrays of subarrays of size lambda. So these are subarrays. M1 prime is the median of this subarray. and so on. Okay, now now we will upper bound and lower bound the size of each part after the partition. So size of parts. So partition divides the array A with respect to the pivot element into two parts, and we will show that both parts can't be too small or too less or too large, and that will mean that both parts should be theta n. The size of both the parts should be theta n. Suppose this is the array A, and after partition the pivot is this element. So this is my pivot. Here what is stored? M prime n by 2 lambda. Let's see which elements must appear in the left part of the pivot. So which elements are definitely smaller than the pivot element? Definitely all the medians m1 prime, m2 prime till the last one are smaller than the median, than the pivot. And not only that, this m1 prime is the median of this lambda many elements. So this lambda, so suppose let's sort these subarrays of size lambda also from top to bottom in an ascending order. That means the smallest element comes at the top and so on. So then all the elements on top of m1 prime, m2 prime, this one and these, all the elements that appear in the green shaded region, they are definitely smaller than the pivot, and hence they should appear in the left part of the array A after partition. So that gives a lower bound on the size of the parts. So how many these blocks are there? There are n by 2 lambda many such blocks, and in each block how many elements, so there are n by 2 lambda many such subarrays, and in each subarrays the number of green elements is at least lambda by 2. Okay. Similarly, what is an upper bound? Size of the part. So size of the left part is size at least this. What is the upper bound? Can it be as large as n? No. Again, some elements by the exact same argument, these elements, all the pivots which appear after that, and all the elements who are larger than this, all the medians who appear after m prime n by 2 lambda, and all the elements below that is more than the pivot, and they must appear on the right. So they can't appear in the left, so the maximum size could be n minus n by 2 lambda times lambda by 2. As you can see that if you ignore these ceilings and this lambda cancels, and the size of each of the parts, so we have proved that the size of the left part is in between n by 4 and 3n by 4, which automatically implies that the size of the right part is also between n by 4 and 3n by 4. So this shows that here is the important thing, that size of each part so we have written this. Now let's write the time complexity recurrence. So Tn is less than equal to the recursive call. We are making one recursive call, and how many elements, what is the maximum number of elements that can appear in the recursive call is the upper bound on the size. This is T n minus n by 2 lambda by 2. This is one recursive call, and we have another recursive call. We are finding median of medians using the recursive call, and how many elements we are passing there. We were passing m1 m2 up to m n by lambda. So we are passing n by lambda many elements there to find the median of medians. And what else computation we are doing? We were doing partition that takes order of n times. So we are writing Cn for some constant c. C equal to big O. C is some constant. Okay, so that is the recurrence, and which basically looks like, if you ignore the ceilings and floors, so you can write that Tn is less than equal to T3n by 4 plus Tn by lambda plus Cn. Now I would let you check that the solution Tn is order n if lambda is greater than equal to 5. If you recall that this recurrence relation appears many times, and this is order n if the sum of these elements, sum of the parameters of recursive calls, if they sum up to strictly less than n, then the additive term Cn dominates and the time complexity becomes order n. So if I choose any lambda greater than 5 or at least 5, then I have 3n by 4 plus say at least n by 5 or at most n by 5. The sum is strictly less than n, and in this case the running time is order n. Okay, so that's enough. So if you pick, for example, lambda equal to 4, then it will become, say, if you pick lambda equal to 4, then this sum 3n by 4 plus n by 4 will be n, and in that case it won't be order n. Okay. Okay, so this also answers the one of the popular question that in this algorithm, if this algorithm does not run in order n time if the subdivision size, the size of the subdivided arrays or subarrays is strictly less than 5. From 5 onwards, it can be 6, 7, 8, 9, 10, any constant, and the running time will be order n. But if it is less than 5, say 4 or 3, then the running time won't be order n. Okay, thank you.